In the real world, the knowledge is not static. Documents don't get embedded once and forgotten. They change, they get updated, get deleted, and get replaced. Documents evolve continuously, and unless your system is deliberately designed to handle that change, the quality of your RAG system will slowly degrade. That's why this video is all about the ingestion pipelines. Up until now in this series, we have been building the foundations the right way. We started by understanding basic RAG, what it is, why it exists, and how the core components fit together. Then we moved into advanced retrieval techniques, where we focused on improving the quality of context at query time, and after that we went deep into chunking. At this point, we have essentially mastered the individual techniques that make RAG work. But here's the catch. Knowing chunking and retrieval strategies and embedding models in isolation is not enough to build a system. Ingestion is the missing piece that ties everything we have learned so far together. It's a system that takes raw, messy, constantly changing documents and applies the best strategies we have already discussed, that are cleaning, semantic chunking, metadata versioning, in a way that stays correct over time. So in this video, we are going to shift perspective. We are going to stop thinking in terms of individual techniques and start thinking in terms of systems. Welcome back to the channel. In this session, we'll design a RAG ingestion pipeline from raw documents all the way to retrieval-ready context. And we'll do it with production mindset, not tied to any specific cloud or framework yet, like LangChain, because we want to purely focus on systems design grounded in the realities of how RAG systems are built and maintained. By the end of this video, you'll understand how to design ingestion that doesn't quietly break the moment your data changes. So let's get started. The correct mental model for RAG ingestion is not ML pipeline and not prompt engineering. It's closer to how search engines, data warehouses, and indexing systems are designed. At conceptual level, every RAG ingestion pipeline follows the same transformation path. It starts with extraction of data from raw sources, then cleaning and normalization, and all the way to semantic or chunking. Then chunks get embedded and indexed. Each stage exists to reduce ambiguity and increase semantic usefulness. Each stage must be independently observable, retriable, and versioned. If any stage is weak, the downstream stages amplify that weakness. Let's understand each section in more detail, and starting with extraction. Extraction is often described or understood as getting text out of the documents, but that description is dangerously misleading. A PDF is not a text document, or HTML is not content. Images have no text. Extraction is the process of reconstructing the logical structure of information. What you are trying to recover is what a human reader would recognize as sections, headings, paragraphs, lists, and tables, not what a parser happens to emit. Consider a policy in PDF. A naive extractor might produce something like this. To an embedding model, keyword company policy confidential becomes a dominant semantic signal. But to a human, it's meaningless noise in this. A well-designed extraction stage produces something like this, which is a well-structured output. This structure is not cosmetic. It directly determines the chunk quality, metadata fidelity, and retrieval accuracy. Once hierarchy is lost, it cannot be reconstructed later. Let's move to the next stage, which is cleaning. When you embed text, you are not storing it passively. You are encoding it into a semantic memory. Anything you embed becomes something the system can recall later. Cleaning is the stage where you decide what is allowed into that memory. This includes removing repeated headers, footers, navigation elements, OCR artifacts, page numbers, watermarks, and boilerplate text that appears in every document. A useful thought experiment is this. If a user or a human skip a line while reading, your embedding model should never say it. Here is a simple conceptual cleaning step in the code. Poor cleaning permanently degrades retrieval quality, and this cannot be fixed with better prompts. Next is chunking. We have already spoken about chunking enough, but just to add a bit more, chunking is not just about breaking bigger documents into smaller chunks. It's breaking them into retrievable units of meaning. Every chunk represents the smallest unit of information that should be retrieved and reasoned over as a whole. If a concept requires context from adjacent paragraphs, those paragraphs belongs in the same chunk. If a question and its answer are separated, the system has already failed. Consider a procedural document A naive token-based split might cut it like this. But a semantic chunker instead produces something like this. This is critical because retrieval boundaries are reasoning boundaries. Embedding comes next in the pipeline, where documents are processed by the embeddings models. The embeddings model converts the text from each document into numerical vectors. These vectors capture semantic meaning of the text, and embeddings allow the system to understand relationship between words on conceptual level. Embedding transforms text into vectors, but they are no durable truth. They are derived artifacts. They depend on the embedding model, tokenization behavior, pre-processing logic, and the chunk boundaries used at the time of creation. This means embeddings have an implicit version, even if you never store one. A production-grade system assumes embeddings will be regenerated. Model upgrades, quality improvements, or cost optimization should not require redesigning the entire system. We should be able to just update the embeddings. This implies a key design rule, which is that the source of truth is cleaned, chunked text plus metadata, not the embedding vectors. Re-embedding should be safe, repeatable, and expected. Moving on to the next stage, which is indexing. Indexing defines how retrieval works. A real index stores vector alongside their text, metadata, document references, versions, and access constraints. Retrieval is not just nearest neighbor search, it's constrained semantic search. Conceptually, a stored record looks like this. Without metadata, retrieval becomes blind and uncontrollable. Next comes metadata. It enables filtering, deletion, auditing, debugging, and governance. It answers the questions users and regulators will eventually ask you. Where did this answer come from? Is it current? Is it allowed? Which document produced it? If you cannot answer those questions, your system is not production ready. Metadata lives through the entire life cycle of ingestion, from extractions to indexing. It's not added at the end, it's carried forward deliberately. We have covered enough theory. Let's look at some implementation details. I'm going to use Dagster UI as orchestrator of our ingestion pipeline. It visualizes the pipeline, executes steps in the right order, captures logs, and makes it easy to rerun or debug. This is why orchestration matters for ingestion. Real ingestion pipelines will fail, they need retries, and we need visibility. This is our ingestion pipeline as a DAG. Each box is a stage, and the arrows show the flow of the artifacts. Okay, let's quickly walk through the repository so it's clear what's happening. Here we have a small project. The goal is to make ingestion understandable and visible. The first folder I'm gonna go through is the rag ingestion. It has a main file named as definitions.py. We'll go through the code later, but right now we'll just focus on the repository structure. At the high level, this file has every stage defined in it as a simple function. For example, text, clean, chunk, index, and the Dagster pipeline wires those functions into a DAG using job definition defined here. So the next folder is input docs. This is the input folder. In real system, you could have something like S3 bucket, a SharePoint drive, a wiki export, but for a demo, we just use text file. This one has a text file with some data in it. So the next folder is artifacts, which is currently empty. It is the main teaching tool. Every Dagster run has a run ID, and we write every stage output into artifacts folder /run ID and then the files. That means we can literally open and inspect what extraction produced and what cleaning has produced and what chunking produced and so on. Next folder is state. State has two files, manifest.json and vectorindex.json. If you have incremental updates enabled, you will also have a state folder. That's where you store a manifest file, manifest of what's already indexed, so you can do true upserts and deletes. Let's look at the main Dagster definition file. At the top, we have some imports and input and output locations. We also have directory, artifact directory location and state directory and few files. Then we have a few more functions to save and load the files from the location. Then we have a hashing function, which is SHA-256 hashing function. Hashing is how you detect change, enforce idempotency, and build stable chunk identifiers. We'll use this more heavily when we add incremental details. Next is a run directory function. We create a per run artifacts folder. Dagster gives every run a unique ID, and we use that to store outputs. So every run is reproducible and inspectable. So these functions are those helper functions to store the files, artifacts into the artifacts folder based on the run ID. Next come our main function, the extract. So this is where the pipeline starts. In extract, we first load the logger, then we read the input file from the input docs folder, all the text files. Then here we are going to produce a structured payload, and then we write it to 01 extracted corpus.json. That would be our first artifact. Next, we clean the extracted text. Here cleaning is intentionally simple for demo purpose. We trim the white spaces, and we split into lines and remove the empty lines, and then we deduplicate consecutive repeats. In real system, it will be a bit more intensive, like you would also remove headers, footers, boilerplate, and OCR artifacts. After cleaning, we compute a content hash. That hash is what lets us later detect changes and only reprocess what's necessary. Then we make it a structured output, a cleaned output, and then we save the output into text and JSON format. The text file is for humans and the JSON file is for machine and the lineage. Next is chunking. Chunking defines the atomic reasoning units your retriever can return. In this demo, we use a simple heading aware strategy, which is for document IDs. When a line looks like a section heading, which in our sample.txt file is refund policy and exclusion, then we start a new chunk. Each chunk gets a deterministic ID based on document ID and content hash. Then we hash the content and write 03 underscore chunk preview dot 03 chunks JSON and text file. The preview file is what we will open to see the chunks boundaries. Now embedding, we take each chunk and generate a vector. In this demo, we use a deterministic fake embedding, so you don't need an API key and the demo is repeatable. But the important part is that each embedding record includes a model, embedding model name and its version, because embeddings are derived data, not source of truth. So if you change the model or chunking strategy, you re-embed, and then we write the data into the JSON file. Then comes indexing. This is where we upsert vectors into database alongside metadata and potentially delete the stale vectors for updated documents. We simulate the indexing by this JSON report. It's called index report. The report is what you would use for monitoring how many vectors were inserted and how many were updated, how many deletes happened, and what the namespace you write into. Then we write the report into this folder and with this name, the JSON file, and that's the summary artifact. Next comes our job definition here. Job at the job, this wires these ops into the DAGS UI pipeline together. Dagster uses this to render the DAG and execute steps in order. This is the core point. The pipeline is simple set of functions, and the orchestration give us the visibility and control. Now let's move to the Dagster UI to see the output of the pipeline. As we saw before, this is the Dagster UI. Here we have one job, rank ingestion job, that we define using definitions.py. Each node here represent one stage, and we can see the full workflow, and we can inspect every stage and its outcome. So let's go to the launch pad and hit launch run. Now I'm launching a run. Dagster orchestrate execution and capture logs in a real world. The run has been complete, and you can see that each stage has been executed, and then we can scroll down to each stage. For example, here you can see it has started the extract, and there is a way to look at the output which says that it has yielded output result of type this, and then it has written it to this particular file. Then we go back to the previous step events again and scroll down to see what is okay. So extract was done, then clean, same goes with all the stages. Then we go back to the VS Code and see what it has written. Now you can see the artifacts. This is our run ID, and then we have all the artifacts added here. First one is extracted corpus. This is the extracted output. Notice it's just the raw text, the extracted text, and the identity, document identity, and the timestamps. This is what downstream stages rely on. The next, the noise is removed, all the text are deduplicated, and the empty lines are removed. So this is very clean to pass it on to the next stages. Next is chunk preview file. So these are our chunks. The file is divided into 2 chunks. Each chunk is a unit of meaning that should be retrieved together. So it also added the chunk IDs. Next is embeddings, embedding file. These are our embeddings. You can see that these numbers. Each line is 1 chunk with embedding vector, the embedding model and its version. This makes embeddings auditable and replaceable. Next file is index report.json. Here's our final report. In production pipeline, this is what you use to monitor the ingestion pipeline. For example, how many chunks were indexed, whether there is any deletion that happened, whether anything failed, etc. Now you might be wondering what these 2 deleted and upserted ones are. So this pipeline is intentionally designed to be document synchronous. That means when a document is processed, we don't try to surgically update individual chunks. Instead, we remove all the previous indexed chunk for that document, and then we re-upsert the current ones. So this approach guarantees that the vector database always matches the current document state, even if the chunk boundary or chunk ID is changed. In other words, we are producing 2 chunks. So the pipeline deleted the 2 old chunk vectors and upserted the 2 current ones. Because the document content did not change, the net effect is 0, but the system verified the consistency. I can run this pipeline once, 10 times or 100 times. I'll always end up with the same final state in the vector database. That's our goal. If the report ever showed growing upserts without corresponding deletes for the same document, that would be a red flag. That would mean duplicate vectors and the silent index is corrupted. So if we go back to the manifest.json file, you would see there are only 2 chunks, not 4. Not if you run it multiple times, there should be always 2 chunks. And the vector index should only have those chunks with their embeddings. In the larger systems, you might optimize this by skipping re-indexing when the content hash hasn't changed, but you should only do that once your pipeline is stable and well tested, because partial updates are where ingestion bugs happen. Okay, so now I'm going to edit the input file, which is sample.txt. I'm going to remove the second section, which means there should be only 1 chunk left. And then I'm going to rerun the pipeline using Dagster UI, and then we see whether our pipeline is adding the incremental deletion and upsert or not. Let's go to the Dagster UI. We go back to the jobs, and we will launch the job, another run, and we wait for it to finish, which is successfully, looks like it's successfully completed. We look at the report. This is our new artifact, the run ID, and you can see the extracted corpus doesn't have the data that we deleted, which was the second part of it. Then the clean text are only this much. We don't have any other heading here. There's only 1 chunk. The embedding produce only 1 document set of embedding, and then the index report says the sample has been changed, the document name. There was 1 upsert and 2 delete. It always delete everything, as I said before, because it's a document synchronous output. Deletes everything and then inserted 1. So if we go back to the manifest, we would see that there is only 1 chunk this time. So this shows that the pipeline is completely consistent, synchronous. So let's quickly recap what we covered in this video. We started by designing a real ingestion pipeline. We walked through how raw document flows through extraction, cleaning, chunking, embedding, and indexing, and more importantly, how each stage produced an inspectable artifact so the system never becomes a black box. We then ran the pipeline end to end and used Dagster to visualize the workflow step by step. We didn't just see that it ran, we saw what came out of every stage, which is exactly what you need when the ingestion starts to fail. After that, we updated the source document. We changed the sample.txt file. We removed the second part of it, and we reran the pipeline. Instead of blindly appending vectors, we saw an idempotent response. Old chunks were deleted and new chunks were upserted. The final state of vector index stays clean and correct. This is what makes an ingestion pipeline production safe. You can rerun it multiple times without fear. You can deploy changes. You can recover from failures, and you can guarantee that your vector database always reflect what the current state of your document is, not whatever happened to be embedded last week. Each part of this pipeline plays a critical role. Extraction determines what content even exists. Cleaning decides what deserves to be remembered. Chunking defines the atomic units of retrievable units your model can reason over. Embeddings turn meaning into searchable representations, and indexing enforces consistency, correctness, and traceability over time. If any of this is weak, the entire pipeline becomes unreliable, no matter how good your model or prompts are. In the upcoming videos, we will build on this foundation. We will add content hash gates to skip unnecessary work, handle true document deletes, and then map this exact design onto real vector databases and frameworks like LangChain and Llama Index. If this helps you think about RAG as system instead of just an API call, hit like, subscribe, and check the repo linked below so you can run this pipeline yourself.